All right, in this screencast, we consider two tests for divergence or convergence of integrals. One is called the divergence test, the other is called the integral test. And neither one is terribly surprising in their nomenclature. So let's look at the nth term test for divergence. What is the nth term test for divergence? Very simply, if the limit of the a sub n's is not 0, then the sum of all the a sub n's diverges. This is as basic as it gets. If the limit at infinity is not 0, then the sum of the a sub n's must diverge. Why? Because if we're adding up a bunch of things, and those things never get infinitely small, then adding them up is like adding up 1 plus 1 plus 1 plus 1 plus 1 plus 1 forever. It has to blow up. It has to diverge. So we could play the very simple game. Do they converge? This will be a very popular game for us throughout our time together. The sum from 1 to infinity of n plus 2 over n. Does that sum converge? Well, what happens to this as n gets large? This limit is 1. And because this limit is 1, then adding them all together is adding up 1 plus 1 plus 1 plus 1 plus 1 forever. No, this series does not converge because adding 1 forever results in an infinite sum. What about this? Well, what happens to this as n gets large? Well, the limit is negative 1/3. And so we're adding negative a third, 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 and that definitely gets infinitely large in a negative direction. I offer the following warning. Let's be clear about what the test doesn't say. This limit is 0. So what's the answer to the question? Maybe. The test is a test for divergence. If the limit is not 0, then the series diverges. The test doesn't tell us anything about what happens if the limit is 0. If the limit is 0, maybe it diverges, maybe it converges. We can't use the test. And that's why there are other tests, and your author goes into this in some detail. Let's take a look at the integral test. And the integral test says we're going to let some sequence a sub n be a sequence of positive terms. We won't let negative terms in for a while. Suppose that a sub n is some function of n for some positive, continuous, decreasing function f. Then the series that adds up all the a sub n's and the integral from 1 to infinity of f of x dx do the same thing. They either both converge or they both diverge. Whatever the one does, the other does. Why? Why does this work? Why does it even make sense? Well, if we imagined that our sequence was Here, 1, 2, 3, 4, 5, 6, like so. If we imagined that our sequence was like this, and we imagined that these points all sat on some continuous, differentiable, decreasing function f. What does the series find? It finds the sum of a1 plus a2 plus a3 plus a4 plus a5 and so on. So that's this area here. Well, that's gotta be related to the area under the curve from 1 to infinity. So if the area under the curve from 1 to infinity is finite, then this blue area should be finite. And if the area under the red curve is infinite, then the blue area has to be infinite. It's bigger. So just by way of example, I think this is example 2. Do they converge? It's a very popular game. Do they converge? Well, this is the sum from 1 to infinity of 1 over n squared. And then over here, we'll do the sum from 1 to infinity of 1 over n. Both of these fail the divergence test because the limits of both of those sequences is 0. So in the case on the left, we will take the integral from 1 to infinity of 1 over x squared dx and see what happens. So this is the limit as b approaches infinity of some antiderivative evaluated between 1 and b. That antiderivative is negative 1 over x. So we take the limit as b approaches infinity of negative 1 over b minus negative 1 over 1, and we get a regular American number. And because we get a regular American number and not infinity, the answer to the question is yes, this series converges. Now, I will note, there's no way that the sum is 1 because the first term is 1. In fact, the sum happens to be pi squared over 6 for reasons that are beyond the scope of our course. It's not that the series is 1, it's that we got a number, and so we get a number. Contrast that with what happens over here. We take the limit as b approaches infinity of the antiderivative of 1 over x. So we take the limit as b approaches infinity of natural log b minus natural log 1, and we find out that this is infinity. And because the integral is infinite, so is the series. Incidentally, this series grows very, very slowly. If you were to find the sum of the first 178 million terms of this sequence, it's about 20. It grows really, really slowly, but infinity is far away from 178 million, and so yeah, it diverges. I will note that both of these are examples of what are called p-series, 1 over n to a power, and these p-series converge if and only if p is greater than 1. And sure enough, p is greater than 1, converges, p is not greater than 1, diverges. We'll do some other examples in another screencast, but this is good enough for here.